Aloha kako, I'm Natalie Marianne Walsh, and my project is Bovidae and bird bioacoustics. I'm kind of a sucker for alliteration, but basically, my project is improvements to a modeling system to distinguish between the sounds made by seabirds and by Bovidae. A little backstory about me, I was born and raised on Big Island, and I'm a current junior at UH Hilo studying biology, ecology, looking at a certificate in data science. Um, I'm a member of the Listening Observatory for Hawaiian Ecosystems, the Lohe Lab, which is based at UH Hilo. I've been with them for about 2 years, and I work as a bioacoustic research assistant, locating and estimating seabird populations on the main Hawaiian Islands. Some interests, birds, of course, conservation and Hawaiian species, and when I graduate, the goal is to work in conservation in Hawaii. My work in bioacoustics really sparked a passion for data science, and I saw the SCIPE program as a really great opportunity to gain some experience in data analysis, programming, and to learn from people inside the field. Um, for my project, I wanted to find a solution to a real problem, um, and I wanted to thank everybody so much at SCIPE. This program really came at the perfect time because I start my data classes in the fall, so it's a little bit of experience for that. Um, Quick run through of some terms. Bovidae is a family that includes goats, sheep, and cows. I group them together because their sounds can be kind of indistinguishable and they're all confusion sounds. The bird we're focusing on is the wa'u or Hawaiian petrel. And then bioacoustics is a field that combines biological principles with acoustic tech to study animal communication, behavior, vocalizations. Um, a little bit more background about why I chose this bird. So Wa'u are only found in Hawaii, and they spend most of their life at sea, but they breed on all the main Hawaiian Islands. You might have never seen them before because they leave their nests at dawn to get fish, return at dusk, and nest all the way in cavities in lava fields, which is pretty inaccessible. So bioacoustics is an essential tool to help locate them because while we can't see them, we can certainly hear them. Um, in my audio searching for seabirds, Bovidae make many similar sounds that an algorithm can pretty easily mistake for a sound of an oahu. Confusing sounds mean listening to like the same clip about 50 times because they really do sound similar. So training a program to distinguish between them would save time and provide more accurate identifications. Our native birds are endangered and at risk of extinction, and in the race against predators like cats, um, to locate and protect the seabird nests, time is really important. That brings us to my question. How can I train a program to accurately distinguish between seabird calls and bovidae sounds? My methodology is how I did it. I used the SCIPE Jetstream 2 allocation to create an instance and attached a 60 gigabyte volume. That volume housed my data for the project and it needed to be pretty big. My data came from the Maui Nui Seabird Recovery Project, MNSRP. We had 33,000 site audio files, 900 Oahu clips, and over 300 Bovidae sounds. And in order to process that amount of data, in my Jetstream instance, I started a Jupyter lab and uploaded 3 pre-coded notebooks. So I got these notebooks from Perch, which is a public repository on GitHub developed by Google DeepMind to analyze audio. The latest edition, Perch 2.0, uses AI to scan, classify, and identify sounds quickly. My 3 notebooks were analysis, embedding audio, and agile modeling. So with the help of my site mentor, Victoria, and my mentor, Amanda Naveen from the Lohe Lab, we adapted those notebooks to the project. We ran into a bunch of issues in the beginning using the Exosphere desktop because of updates to the notebooks. So we eventually moved it on to attaching it to my physical computer IP address, and that fixed everything. For the data collection itself, uh, they allowed me to use their private audio recording, so it's not a public data set. MNSRP utilized passive acoustic deployment via song meters. So on the bottom right is a picture of a song meter. It's basically a large waterproof microphone. It stores audio recordings on really large SD cards. So a site is a location of a song meter. And out of the data set provided by MNSRP, I isolated 4 sites that contained both uau and Bovidae confusion sounds. So sites 1 and 2 were deployed from the start of May to mid-September, Site 3 from the start of June till August, Site 4 from August till late September, and all those sites are located on West Maui, indicated on the map by the red star. Okay, so after I uploaded all the data, I got started on processing. Um, I took the audios and ran them through the embeddings notebook, running the Perch 8 model, which was designed to process bird sounds. This notebook made it so that similar sounds had similar vectors, making it much easier for the model to process. After that, the Agile modeling notebook ran through the sounds and created a model with custom classifiers for targets. So by classifying these sounds into groups, like Woe class, Bovidae class, and Silence class, you can choose to search for those sounds or eliminate them from your search. Finally, in my analysis notebook, I did precision modeling searching for Woe audio clips. A little more about that. Inside of the analysis notebook, I searched for the top Woe clips, what the model deems to be the best of the site files, based on the clips that I trained it on. So I sorted through 100 5-second clips per round with 3 rounds per site. I was able to do this using spectrograms, which are basically a visual representation of a sound that are generated by the notebook. On the bottom left, you can see a pretty classic what we'll call the call that they're named after. And visually, I think it kind of looks like a golf club. At the very edge of that same spectrogram, you can see the start of a sheep call. So it's kind of sneaky, and while spectrograms allow us to easily glance at an audio clip and recognize it, looks can be kind of deceiving. These spectrograms are of all the confusion classes I created in the Agile Modeling Notebook. I have Bovidae to get rid of confusion sounds. I also have another Uau call just to show how similar they look, and the Silence class, which getting rid of that filtered out a lot of really just blank clips. Um, Finally, we have data visualization. So these are the 3 rounds that I ran. Round 1 was my baseline before applying all the classifiers, and round 3 was after adding every classifier, which was cow sounds, goat sounds, and the silence sound. This basically improved the model's ability to filter out confusion sounds and the blank audio clips. The first 3 sites were marked as abundant for Oahu, meaning over 50% were of a random selection of the samples collected at the site were positive, I think that's responsible for their huge increase from 11 to 86, from 29 to 99%, because they had more Oahu to start with compared to Site 4, which was not marked as abundant. And because each site is at a new location, they may encounter different confusion sounds, which is why I grouped cows and goats together, because while goats may be present at one site, they could be absent from another. Let's see. So to wrap it up, my next steps for the project would be to continue refining the model with the Lohe lab and finding other confusion sounds. Um, and thanks to the site program and their team of mentors and the workshops led, I learned about instance and Jupyter Hub building, tailoring Jupyter Hubs, and high performance computing with Koa. This is a huge learning experience for me because it was my first data science research project. And when I started, I saw every single error message as like a blockade. I was like, okay, we got to shut it down. We got to start a new project. But with experience and help, I learned that they're really just there to tell you what to fix, which was pretty much everything. I'm really excited to see what other projects I'll do. And I know that cyber infrastructure is the future, and bioacoustics is just the beginning of possibilities, especially for conservation work. Um, so I wanted to say thank you so much to the Hawaii Data Science Institute and UH of Hawaii for creating the site program, Dr. Alex for running everything, NSF and CI Pacific professionals for the grant, Maui Nui Seabird Recovery Project team for collecting all the audio data and allowing me to use it, and then the Lohe Lab and everybody in it. Of course, Amanda Naveen, the Manta 3, my great cohort, they're very, very supportive. And then I'd also special shout out to Amanda with the Lohe Lab and Victoria. This project would not have been possible without them. All right. Thank you so much. My email's there, my GitHub's there. It'll have a breakdown of the project and more details. Thank you.
That's very cool. Thank you very much.